Okay, in this video, we are going to look at the FM21 paper 42. Okay, and we're going to start with question 1. So if you have yet to try the paper, I highly recommend you try the paper first so that you get a preview of how you would do if, let's say, you were to receive a paper like this in the exam. All right. So in question 1, it says here, state Newton's law of gravitation. So this is very standard. Okay, I'm going to type out the law instead of writing it. So this will be the force or the gravitational force between 2-point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation. So oftentimes, right, when it comes to definition in A2, they are a little bit more technical compared to AS because, you know, you are smarter now, right? So always when you're asked to define something, either relate to an equation or a diagram or both. So for me, when I see Newton's law of gravitation, immediately I think of this equation, GMm m2 over r square, okay? Where you have mass 1, mass 2, okay? And the separation is r. So I will write this, but you know, whenever there is law, we will talk about proportionality. So when we say this force is proportional to the product of masses, which is m1, m2, product of the masses is m1 and m2, and inversely proportional to the square of their separation, that would be your r square. Okay, this whole thing is 1 mark. What is the second mark? And this is probably your M1, meaning you need to write this first. Your A1, which is the final mark that you can only get if you get your M1, is if you mention that this is 2-point masses. So I don't care whether it's a sun and the planet Earth or the Earth and the tiny moon in this scale. We are assuming that all of the mass is concentrated at the center. So it's the idea of this thing being a point mass. So here we see that there are planets observed orbiting a star in another solar system. Okay, I'm also going to try to find where this question is from because I recall a very similar past year question. Do you? I can give you bonus marks if you actually know which year this is from. Okay, too late, I found it. This is from ON15 paper 43 question 1. So a lot of times, right, students will think, okay lah, I just do the 2020 paper and I'm set for 2021. No, friends, you know or not, they like to repeat paper from like 5 years ago, 10 years ago, 4 years ago. So have you done papers from that era? If you have not, you got time. Go and do a few. Try to get a feel of how the question changes across time. Because they may have certain period one. Okay. So anyway, you can go and look at this question from ON15 paper 43. It also has this graph or a similar graph. It's not identical. So in the paper 43 version, the graph is x cubed against t square, and t square is in days. Here, the graph is t square against r cubed, which is distance. Okay, so go try this question after you watch the discussion. All right, to make sure you understand. So this is the variation of r cubed and t square. And what are we looking at? We have planets orbiting a star. Okay, draw diagram. We have a star. Does my star look like a star? Okay, I don't know. All right, and then we have planets, a bunch of planets. Okay, the orbital radius is r. So measure from the center of the star. This is your r. This is maybe planet 1, maybe this is Mercury, this is Neptune, I don't know, maybe this is Earth. Okay, and they are orbiting around the sun. So it's R1. So it has its own period. And then here to here, you will have R2. It has its own period. This is its circular orbit. Okay, and then maybe For this third planet, this is another circular orbit, and here to here, this is your R3. So we observe a bunch of planets and we plot their period square, the period of the orbit, against how far they are. Let's see if this graph makes sense or not. The further away you are, the bigger the R cube, the bigger the period. Makes sense, right? The further away you are from the sun, the longer it would take for you to orbit one round against the sun. So if you are not sure about what period is normally when you have one complete cycle. In this case, it is the time taken for the planet to orbit the sun. So to move in one circle around the sun. So you have this graph, it's a beautiful straight line, very good. I don't know what they want from us, but let's continue. The relationship between T and R is given by this equation, where G is the gravitational constant and M is the mass of the star. So for the purpose of exam revision, when I see this, immediately I think about the fact that I need to know how to prove this. You need to know the proof. But the good news here is, let me steal a line from one of my students. Miss, all the question with the planets one, we can use centripetal force equal gravitational force. One question to rule all the circles. Because here you can put mr omega square, and this is the gravitational force GMm over r square. Just to again give you a description, this m is the big one. This one is the small one that is moving in a circular orbit. Okay, so if we very quickly do some rudimentary rearrangement, I will get omega square is gm over r cube, and omega is 2 pi over t. So 2 pi over t square is gm over r cube. I changed to capital R because they use capital R. So if I rearrange this equation such that t square is brought up, okay, what I have now would be 4 pi square r cube over gm. Okay, so it's just algebraic rearrangement. This proof, normally if it comes out, is 3 marks, but they didn't ask you to prove. I'm just telling you in case you're asked to prove. Okay, determine the mass m. So when you are given a graph, right, like this, okay, try to use things like, if possible, gradient or y-intercept, if possible. So in this case, I'm just going to look at this. I plot a graph of t square against r cube. T square against r cube. So if I compare with the general equation, y is equal to mx. There's no c, so y-intercept is 0. Indeed, because the graph passes through the origin, you will see that your gradient m is equal to 4 pi square over gm. This is always the first mark. You announcing boldly to the question or the examiner, hello examiner, I am a smart kid. I know gradient is 4 pi square over gm. Mic drop. Mic drop, point drop, you get C1. Start with this, because who knows, maybe you make a mistake somewhere, right? So it's more like, hi, get the insurance first, get the first mark, okay? Then we find gradient. Be very careful, because I see strange units on the axis. Look at this year square. Why plot year square? Means we have to convert, meh? Yes, my friends, whenever you see a constant like G, or any physical constant, whenever you use any numbers from this list, everybody else that is sharing an equation with this number have to be in SI. Okay, so we need to convert. Okay lor. So I'm going to draw a triangle. I will start with corner plots, okay? So I like this plot here. This plot looks like 0.4. Don't forget there's a prefix here, times 10 to the power of 34, comma, 0.8. Year square. Okay, noted. Okay, I can take this point, I guess. This point is good enough. So this would be 1.2 times 10 to the power 34, comma, 2.4 year square. So if I want to find gradient, I will take y1 minus y2, x1 minus x2. Or in other words, 2.4 minus 0.8. This one is year square. So I'm going to first write here year square and then I'll convert later, divided by the x1 minus x2, which is 1.2 minus 0.4. Don't forget to inherit the prefix from the axis. Okay, very important to be careful and make sure everything is converted. This one is meter cube. Okay, at least you don't have to convert the denominator of your gradient. Okay, I know you can't do this in your real exam paper, but I can. And you don't have to, because you can actually see the whole paper without scrolling. Okay, so I have this, and obviously I can't continue with this until I convert some units, right? So this will be 4 pi square over GM. Next order of business is to convert the units. So 2.4 minus 0.8, that would be 1.2. But we need to convert 1.2 years to seconds. Are you ready to convert years to seconds? I took 1.5 years to study A levels. How many seconds is it? Okay, so 1 year is 365 days. 1 day is 24 hours. 1 hour is 3600 seconds. My dear friend, do not forget your square. Your square cannot just suddenly go for a walk. Year square. See this? See this? Okay, so this is what I'm converting. This whole thing is here. Okay, so 1.2 minus 0.4 will be 0.8 times 10 to the power of 34. I can substitute everything already. Here is 4 pi square. G is 6.67 times 10 to the power of negative 11. And you can find the value of m. Okay, I am going to only one time, I guess, for the duration of the paper to calculate or show people how to press this during the exam. And I do so because sometimes I see student press calculator, I also stress. Okay, let's say you have this situation here. I am just going to leave m here as 1 over m, and I will begin to transfer values to one side. Okay, you can choose to do this slowly, but that would necessitate a lot of copying, and a lot of copying probably may mean some transfer error or you make some mistake somewhere lah. So this is a method that you can use. So I'm just typing whatever I see on the left hand side, divide by 0.8 exponent 34. So we're going to multiply by 6.67. I hope my calculator don't crash. Negative 11. Divide by 4 divided by pi square. So this one is 1 over m. Then I take 1 over answer. Okay, so I will get something like 3.96 or 3.97 times 10 to the power 30. So pressing like this means you don't have to keep copying all these very weird looking numbers and spend a lot of time here. So I'll write down the final form. This will be 3.97 times 10 to the power of 30 kg. Of course, you can round it to 2SF, so this will be 4.0 times 10 to the power of 30. Okay, this is not CIE's mark scheme. This is where I think the marks should be. Okay, I think there will be an answer, A1 mark. And then if you write gradient is 4 pi square over GM, or you find gradient, if you find, I look at the working, it looks like you're looking for gradient, you will get 1 mark. And everything substituted, including the conversion, is C1. So if you've forgotten to convert, at least you can get 1 mark if, let's say, you write the first line. Okay? So that would be the calculation part. Part C. A rock of mass m is also in orbit around the star in B. Okay. Explain why the potential energy of the rock is negative. So this explanation is very standard. We are explaining why gravitational potential or gravitational potential energy is negative. So to explain this, we start off with the fact that at infinity, the GPE is 0 because there's no field there, so there's no energy. So I will say at infinity, to save time, I'm just going to call this GPE, okay? GPE is 0 or is defined as 0. Okay, second point. Since gravitational field is always attractive, work is done by the field, or you can also say work got out, because that is what they like to use sometimes in the syllabus. So work is done by the field or work got out when a rock is brought from infinity to the orbit. So GPE decreases from 0 and is negative. So when I'm drawing this, I'm thinking about the GPE graph. The planet is here. You want to bring a rock from infinity. The GPE graph would look something like this. It goes down this way. Okay, so if work got out, it just means that you start from 0 and you need to decrease. GPE decrease. The only option is to go down. All right, standard explanation. At infinity, gravitational potential energy is 0 is probably a B1 mark. Okay, you understand that G field is attractive, probably B1. Okay, and then work is done by the field or work got out when the rock is brought from infinity to orbit. This is B1. Normally, this one is for your brain because gravitational field is doing the work, so its energy will drop. And it drops from 0. That's why it's negative. This is for your brain, less for them. Okay, show the kinetic energy of the rock is given by this one. Oh, no wonder there's no show in front. Okay, so you want to find the kinetic of the energy of the rock. This is half mv square. Okay, so we need to find half mv square like my student last time told me in 2019. I'll forever remember. You can start with this one. If you don't know what to do, start with this one. mv square over r. Centripetal force provides the necessary gravitational force for the stone to be in orbit. So the mass, I mean, you can choose to start cancel, but you see this half mv square here, you see this half mv square here. Ooh, I like this. So what I'll do is I'll multiply by half mv square here, and then I will multiply half GMm, and then this r can cancel off. One of the r can go away. Okay, over r. So finally, I can say hence, Ek is equal to half mv square and equal to GMm over 2r, proven. So if I were to guess where the mark is, if you start off with the statement or the equation, centripetal force provided by gravitational force is C1 mark. Okay, you writing the right centripetal force equation and the right Newton's law of gravitation equation, and you simplify it correctly, would be another C1, all the steps. Okay, use this expression to derive the total energy of the rock. So if you want to find total energy, you will take the kinetic energy plus the potential energy. So our kinetic energy is already GMm over 2r. Potential energy, recall, will be negative GMm over r. You can go to the playlist if you've forgotten the 4 pillars of gravitational field. Right, so what we have here is half minus 1. If you cannot, I factorize over r. Inside here would be half minus 1. So your answer would be negative GMm over 2r. So I think if they see Ek plus Ep, they will, if they are nice, you will get your C1 here. Okay, and then you substitute the right potential energy equation, leading to the final answer. This would be your A1. Okay, this is not the CIE mark scheme. This is just me stating that if I'm marking the paper, here is where how I will award the marks to follow the bracket. So this question in its entirety is 12 marks. It's a pretty inclusive question. We went all the way from period, okay, the period of orbit, analyzing the graph, to looking at the potential energy. So if you want a question that involves potential energy, sorry about that, if you want a question that involves potential energy just to try out, you could refer to this year ON 15, paper 41, question 1. Okay, so this is a suggested question that you can try. Give it a look-see if you want to practice your idea of gravitational potential energy. And Feb March 17, paper 42, question 1. Alright, so that's it for question 1 from Feb March 21. Well, hello, I noticed that I made a mistake, or rather someone in the comments told me that there's a mistake, so I am re-editing the mistake to make a correction. Did you see the mistake during the live stream? Did you see the mistake when watching the live stream recording? If you did, well done. This is when, I don't know what happened to my brain, you know those moments where you go like 2.4 minus 0.8 is 1.2. Nani? This one is supposed to be 1.6. Repeat the calculation again, okay? And to find the value of m. If you find that this is too risky, what you could do is you could always do something that looks like find the gradient separately, like so. And after you find the gradient, you substitute inside here to find the value of m. That's also possible. So when I do so, I will be able to get the answer of m is equal to 2.98 times 10 to the power of 30 kg. So always in paper 4, if you can, give yourself extra time to go back over and look through your questions again. If you notice a mistake, you can still cross out. Well, you don't have to circle this. So if you imagine this is the actual exam, what I'll do is I will cross out the wrong one and put the right one. And for the value of m, I'll just cancel, cross it out. Okay, so that's it for the question. And thanks for watching. I'll see you in the next one. Bye-bye.